little bit, the link now is a little better organized. So again, I'm encouraging you, because I'm not going to assign a lot of homework in this last lesson, but I encourage you to go through some of this number of this link yourself. Right? We kind of went through this introduction, brain power, alpha zone, so that gives you broader perspective of where this neural network, deep learning, and AI coming and where it's going. And what I want to do today is now go to very elementary, deep into very elementary things about the neural network to show you actually what's the basic understanding of the neural network as we are talking about today. And then in the next 2 or 3 lectures, then using, we go through this particular go through this practice example of image recognition of handwriting, which is a classic example of where this field really in recent years, about decades ago, taking off, is to able to really recognize the handwriting. Let's say simplest task would be just the handwriting of a digit, and it used to be very difficult. And it's a problem which is studied for decades, and the machine was never able to come close to human being. But ever since this convolution neural network and the deep learning got implemented, and 10 years ago they basically gradually improved, and very quickly it become very good as you pass the human. So it's simple enough that I hope that we are able to go through that and get you some idea. Really, after going through this, you actually should able to construct a neural network and write a code and to do reasonable tasks of whatever you are interested in. But that this practice module is based on Python, and particularly is a PyTorch. So I would like you to go through this Google Collab and PyTorch tutorial yourself on your own time before we start the next lecture. Go through when we get to handwritten hand digit recognition using PyTorch, and that's where we go through in a little bit more detail. But these two are just simply skill which you should be able to pick up yourself. Okay, so now with that, then we go through today, which is neural network and deep learning. So this is what we are going to through, and this is an online book, and I have a link here. So it's actually you can read it. It's online, and it got many chapters. And in fact, it started with also using this handwritten recognition as example. So, our human visual system, right, is in fact is actually very complex. When we look at this string of letter, we can able to identify this is 504192, and most of us can do this easily, right? And you think about it, what really make us good in this sense. It's not like we are born able to recognize the digit. In fact, our brain been trained ever since we were born. Our brain, as you remember from last lecture, is basically a complex network of neurons with a weighting, with a synapse, which is connecting different neurons. And they, when child is born, it's already get this tremendous complex network connect to each other, but the weighting doesn't have much meaning. And those weighting or communication or snap between the neuron develop meaning because we are constantly stimulated by the external sensory, and then constantly being taught what is good for us, what is bad for us, and what we should know and what we should not care, for example. So You know, when we start learning alphabet, for example, or start learning number, and then it gradually feed into it. Of course, you know, you have been read many books, for example, with your parents or your grandparents, and those training go into your neuron, and they reinforce your brain, and soon you're able to recognize, you know, individual digit 1 to 10 or 1 to 9, 0 to 9. That's the first thing test a child will learn, is to recognize digit. And you know, you just can't imagine actually how many reinforcement learning actually going into that stage. So the understanding neuron, as I said in last lecture, is, you know, the basic function of neuron is kind of well understood it even 10-20 years ago. It's a question of how network working, which it did not quite mature until about a decade ago. So if we look at the individual neuron, the cruelest example is something we call perception. Okay, the perception, you can think about it is as a simple, you know, you can think about it as a logic gate. For example, you can think about, okay, I have this is a this is a logic gate. I have 3 input, x1, x2, x3, and then this could be or could be n, and then there's output which could be 0 and 1. So if x1, x2, x3 is 0 and 1, and going through this operation, you get another output, right? And this output can be then connected to other elements. So in essence, our electronic circuit, right? Our electronic circuit, in essence, and in also in GPU, CPU, which is binary based, is really based on something just like perception. You go to fundamental level, that is just like perception. Right? Let's take a simplest example of how we make a decision. For example, let's say you're making decision. Say you want to take your girlfriend out for dinner today, tonight, for example. Let's just say that is a simple example. And then maybe there's three things which determine that event, whether you're going to take your girlfriend out for dinner or not tonight. Can you think about 3 things which may be relevant? Give me feedback.
Coronavirus.
Oh, what is coronavirus? Okay. Okay. What else?
If you have anything else to do.
If you have anything else to do, right? It's whether your schedule allow you to do it or not, right?
Yeah.
So that's one thing, right? Whether your schedule can allow you to do it. What else?
If you have the money.
You have money, very good. That's the second condition. You have money. 2 conditions. I wanted 1 more condition.
If it's a nice restaurant or something,
Nice,
you know.
restaurant. Okay.
You know,
It's another very important condition you should not forget. Yet, you remember, you're taking your girlfriend out for dinner.
Do you have a girlfriend?
Do you have a girlfriend or not? Okay. Some cases you have girlfriends. But it's just like Brian, what you said, you know, whether you are able to, you're free or not, right? You need your girlfriend to be free, right? So that's a necessary condition. So we simplify the very basic things. So let's think about it. Yeah. So here's I have a simple model. 3 conditions, right? X1 is to say you have money or not. Right, so that's the number. X2 is to say whether you're free, right? And the X3 is to say whether your girlfriend is free. The girlfriends. Oh, it's a misspell. Girlfriends. Is that make sense? 3 conditions, right?
Yeah.
And then we want to do 3 conditions. So I make this in an array. Okay, so that's the input parameter. And then the input parameter had to fit into together to decide. Okay, so the simplest thing to say, I take these 3 input parameter, and I make a weighted sum of these 3 parameter. Let's say the 3 conditions are equally important. So I have this weight, which is 1, 1, 1, and then this numpy dot is simply take this vector and the dot product this vector, right? And that determines the outcome. So outcome is a number, depend on 3 input and with this 3 weighting factor, right? So you might think, okay, with that, then then I make decision. You know, if this is greater than 0, I say I go for dinner. If not, then it's bummer. So suppose you have money, you're free, your girlfriend free, and let's run it. You say yes, let's go for dinner, right? It seems to be everything satisfied, right? That in essence is a perception. Okay, I simply make a binary decision. You know, whether this all is considered now. Suppose they say you don't have money. Okay. And they still say we go for dinner because my calculator may 0 1. Now you may argue this is still plausible. Maybe your girlfriend has money. Maybe you can ask her to pay, right? So that's one plausible. So that still actually makes sense. Let's say, okay, you have money, but you are not free. Now it still can give me say yes, that's good. So that's clearly this simple, what a simple things is doesn't do it right? That means this weighting factor can't be right. So I would like to be able to say increase the weighting for whether you are free or your girlfriend free to much bigger, because you two need to have to be free in order to do. So I'm just saying maybe I should increase this weighting factor. So I'm increasing whether free or not to be a weighting, to be higher weighting factor. Now I still get to go. So you can say this is not good enough. You know, even increase the weighting factor, but my net result is still give me 1. It's basically say so. The additional things I can impose is impose a weighting factor, a bias, so-called bias. Let's say I put bias as a -1, and this is a bias factor. Bias. Now I put a bias. Now if this is the case, that's not good enough. So let's say put bias as 2. Did I get something wrong? No, I didn't add a bias here, so I need to add a bias. Yes, add a bias. So now my outcome is input weighted, right, and plus a shifting with a bias factor. So that is a. Now you can see if your girlfriend is not, if you are not available, is a bummer. You are available, and your girlfriend's not available, it's also a bummer. If you say, okay, they're both available, but you don't have money, you still say yes, even with that bias is yes. But you can see, in this case, the Z is equal to 1 compared where you have money, where the Z is greater, is equal to 3. So you think that in a probability of going to dinner with Z equal to 3 should be different from probability of going to say Z equal to 1. So this is simple binary decision tree with a binary input. It's clearly a very close approximation, a very poor approximation. So what you really want to do is to say, okay, you want to make this x1, x2, x3 as a continuous variable, and then you want to make this output Z also a continuous variable, which essentially gives you some kind of probability type of construction. So it can give you some probability type of things, and that is basically the model of the basic neuron. So if you think about our neuron, is actually it's received the input from many other neurons, which give you a spike train. It's actually it's analog signal. It's not digital signal, and then it's synthesize this input from into a particular neuron, and then it determines whether it's fire or a signal or not. And when it's fire signal, it's actually give you analog kind of output. It's a continuous pulse, short pulse. So, and then the evolution going to this simple perception type of things to the continuous variable is, so I'm going to quickly go through that, is become a so-called sigmoid neuron. Okay, so that this is the underlying basic element to all the neural network. Okay, it's a sigmoid neuron, which of course in some more modern version of this, actually they simplify this a little bit to make computation fast. But this is, in essence, is what going into. So sigma neuron is basically say now you have this input parameter, and then the output is actually continuous variable. So input and output. So this is some kind of function of a 3 input, and this function give you, and this function is very much, you want to make things very simple. The simple things is some kind of weighted sum, linear weighted sum of this input and with bias factor. That's what I just showed you a minute ago. And what it does is instead doing a binary output to say, 0, 1, you output is determined, give you a continuous variable, and then this continuous function is genetically called sigmoid function, which is given by this. This function has if you look at this function, sigma z as 1 over 1 plus z e to the minus z, this function itself, number 3, has this shape. Okay, so when z is very, very, very big, of course e to the minus z is, when z is very big, think about it, when z is very big, e to the minus z is a small number. So therefore, the sigma z is essentially close to 1. So we say probability is 1 if we interpret this probability. When z is very small, and in fact, when z is a negative, when z equals 0 is exactly half, it's kind of now yes or no on the borderline. Then when z is a negative, then this quantity can be very big, right? When z is negative, this quantity can be big. Then sigma z essentially will go to 0. So the probability going 0. So that's basically what this function, sigmoid function look like. Right? When z is large, it's essentially close to 1. When z is negative, it's essentially close to 0. And in between, the z equal to 0 is exact half. So this is a continuous version, if you want. This is a continuous version of the simple step binary function. You say either 0 or 1, 0 or 1, right? Make sense? So that it give you, so I have here this is sigmoid version of these things. So this function it defines 1 over this, and I still have 3 input, still has same weighting function, and I haven't implemented a bias yet, but to say without bias for a moment. Well, in fact, we can put the bias here. So we say bias equal to 0 for a moment, and then let me say plus a bias. And then I'll get z, and then z get transformed to sigma z. Okay. Now this z is a continuous variable. Now I can say this is now it's a probability. Say if the probability is greater than half, we say we go to nil. If the probability is less than half, then so we don't. So let's say if I run now with the same 1, 1, 1 input, and the even bias is equal to 0. Yeah, sure. So we say we go to nil if all the conditions are going to satisfy. But let's say if one of them is not satisfied, let's say suppose one of them is not satisfied, so it's a -1. It's still good, right? It's still good. But if there's another one not satisfied, and so let's say if you're not free, And well, this is not very good. So you want to say, I want to increase the weighting factor. Increase the weighting factor for whether you can go to dinner or not. Presumably. Now, if I run that, well, did it change? It did not change anything.
Honestly, it doesn't look like it.
Wait a second. I must be get a typo. No, the probability did change, right? So
Okay, you must.
probability did change, but the decision is still same. So that means the bias is not. So we need to put a little bit bias there. So I put a little bit bias. So maybe now. So I put it a small bias, and now you can see. This now you say, okay, if one plane is not able to go, then yes, it's a bummer. Or if you say now, suppose I don't have enough money, that is still good. Yeah. So this is essentially the very basic elements which go into the neural network. Is that clear to you guys?
Yeah.
That is the basic things, right? Okay. Now to build a network, what you do is, of course, is simply say, that's a very important factor, is to say, I just build up a network through layer by layer. So I may have, this is a analog, this is a digital version by building. So basically say, I may have input into certain neuron, and this neuron, of course, will give output to other neuron, and then I can build a layer of these things. Make it complex, make this complex. So I could have some more complex. So here is a complex version. Is you have input, go to intermediate layer, and then you could have another intermediate layer, and eventually all this things synthesized into one output decision. Okay, one output decision. Right. So now your output decision clearly depend on the two things, right? One thing is what is the input, obviously x1, x2, x3, x4, right? The other one is this weighting factor W, which is how this get propagated, input propagated to the next layer. And then by weighting factor, I'm including both weighting factor and a bias, which basically is the parameter. You think about this W just represent a parameter in this network, right? Now in this simple case, for example, you have 3 input, 4 intermediate layer, and 1 output layer. How many parameters are there in this network? If I can consider that each connection has a weighting factor, and then each neuron has a bias. How many parameters I have in this simple neural network?
It would be
Any
like
guide or response?
it would be like 2 per line. So in this case, each one is like 4 times 8 times 4. So wait, why?
I always say 8 times 4. What other people answer?
Hang on a second. That doesn't really seem right. No, wait. I don't know. Bias.
Well, if each neuron has a weight and a bias, or if each connection has a weight
Each connection is a weight, each neuron has a bias.
Oh, okay.
Okay. So each connection. Okay.
So you would have there are 12 connections in the front here plus 4, so that's 16 connections, each one with a weight, and then 8 biases, so 24.
Well, oh yeah, 8 biases. Yes.
You sure there's 8 bias?
I think there should be 8 biases, because if the biases are like solely on the neurons.
No.
Okay.
I think your connection, yes, there are 3 times 4, 12 plus 4, so 16 connection. How many buyers in this network?
Do you not have a bias for the input neurons?
That's right. The input is just input, right? You already have this input, so there's no bias going to the input layer. All right. So there are only 5 buyers. Okay.
Okay.
So in this simplest network, we have 16 plus 5, we have 21 parameters. Right? We have 21 parameters. So you can think about this parameter as just a giant vector, right? Input is one vector. Parameter W, that's called generalized W, is another vector, and the output, let's say for the simplicity, just one number. Right? So this one number depends on the 3 input, depend on a 21 weighting parameter, right? So basically how neural network work is to say, suppose now let's say what I do is to identify an input, this 3 input to say whether I go to dinner or not, okay? I have whether I'm available and I have met I'm available, girlfriend's available, I have certain amount of money. Now we're going to transfer this into not a binary. We say, okay, maybe I have 70% available tonight. Maybe she has 50% available tonight. And then maybe I have $50, or maybe my dollar, I had 90% enough money for dinner, or 20% enough money for dinner, right? Now, and then from that, you make a decision. Okay, now you start with these things as kind of random. You started these things with a random connection, okay? And then, of course, initially, when you put this 3 parameter in, you just get a number out, which may not be correlated to actual decision or not, right? You get a number which is larger than 50% or less than 50%. You don't know. So that number, so what do you do? What you do is you look back your dating history. Okay, assuming you have good enough records, this is what we call data. That's why the data so important. Suppose you have been dating your girlfriends for a long time, and you keep meticulous records of what you did. Let's say, if I have $50 and 70% availability and 50% availability, that particular outcome is going to dinner. So imagine you have a lot of this data, right? So you have hundreds of this data. Then you can train this network to say, given that particular condition, the outcome is going dinner or not, okay? And then with that outcome, if this outcome is actually does not fit with your history, then you say, I'm going to go back to change this weighting parameter, okay? So basically, you calculate your outcome compare with your known result. And that is a difference, and that difference is calculated as error. That error is a function of the weighting factor. You can, now since all this weighting factor now is a continuous function, is a continuous variable, this outcome is in principle a continuous function of this weighting factor. Then you can calculate the gradient of this, the dependence of how this outcome depend on this weighting factor, and then you can do the correction. Right. So if initially this network does not give you right prediction to say you should go dinner or not, and then with the sufficient history data, you have sufficient data to train this network, and every time you do this thing, you slightly modify this weighting factor such that outcome actually consistent with your dating history. And if you do enough of these things, then this network gain the proper weighting and the bias, and the outcome is consistent with your dating history. And then now tomorrow, say, okay, you have 50% chance to go to dinner, and you have 80% chance your girlfriend's availability, and you only have 50% chance you have enough money or not. And here is what you want to make a decision. Should we go or not? And then you can fit in this network based on history. If your history is, say, your girlfriend's more likely to pay, then probably you come out say, go for dinner. that is in essence is this neural network, how the training a neural network work. Do you guys get the essence of this?
Yeah.
Yeah.
Yes.
So you can see there's an important, very important three aspects of this thing. One is, of course, is that you have enough data to train a network. That's why data is become a very valuable commodity. That in all this artificial intelligence, in machine learning endeavor, you need enough data to let the network. And this kind of network is what we call enforcement learning. You know, we have plenty of data, and that network learn by enforcement. Right? By enforcement, we enforce the network to learn according to the history, according to existing data, where we know it's yes or no. For example, if this is, for example, input image, whether it's an output to say whether it's cat and dog, you can have plenty of those image, and then you know manually with human coded to say this particular image is a cat or dog, and then if you do 100 or thousands or millions of that, then you can create a network which is able to recognize whether it's a dog or cat, and in fact that can be very accurate. And then if you generalize that to medical imaging, let's say you have plenty of data of a cancer patient data, and you know that particular patients, you have a biopsy which actually is definite prediction whether is cancer or not, and you can train this network to recognize those particular pattern. And you can also now imagine these things can be developed to do all kind of prediction. For example, the virus which is now infecting over us. You know, if you have sufficient history of the outbreak in similar virus outbreak, and how the system propagate, you can kind of predict and create a network with artificial intelligence to predict this outcome. So that is in essence is what a network is doing. All right. So there are so this is a basic things. The key important is that you're able to. So number one, I already said. Number one, you need enough data. Number two, what is make this network actually in the modern version, which is very easy to do, is to calculate this gradient. Namely, the output, the dependent output only this weighting factor, the weighting and the bias. Now our simple network, which I just showed earlier, you know, just with 4 intermediate neuron, 1 output neuron, you already have 21 parameters. Many of this network now has millions of neurons. It may have tens or hundreds of layers. Then you can imagine a number of parameters is tremendous amount. So this calculation of this quantity and able to so-called backpropagate is able to calculate this quantity efficiently and implement it. This is what, in fact, what is modern computation and the algorithm breakthrough is really make this kind of calculation feasible and fast enough. So that is in essence is what. And then the third thing, of course, is to say you have the good architecture of neuron. It's important because it still would gain you efficiency. Okay, so this is basically, you know, this is simple network, input, intermediate layer, output. And of course, you can generalize this to say input, I have many hidden layer, and then 1 output layer. Okay, so this is genetically what the neural network is doing. So now when we later on, not today, in the next lecture, we're going delve into a little bit detail of this. This is time for me then to create a a video to, because some of them of course doing much better lecture. So I'm going to play this one. What is neural network? Chapter 1, deep learning, and then there are some technical detail about the gradient descent, and the backpropagation is the second and third part of the video. And I will encourage you to watch yourself. Okay, watch yourself. So we're going to play the first one here.
I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly.
Politics has constantly been changing. It's exhilarating. It can be
I mean, this, and this. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants. But in these two introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain, but let's break that down. What a 1 for white pixels, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is...
So the key thing here is just give you some kind of intuitive understanding whether actually complex network where you have a lot of layers, a lot of neuron actually doing this or not is something which we really actually don't know. And that's still very much of a cutting edge of research. It is exactly what's going on in this black box of neuron network in between. I think it is, you know, this is just one plausible intuition, but in reality, what exactly going on is still what some kind of mystery, actually.
There's a hope that we might have, a sort of goal edges into pattern. All of those activations from the first layer and compute their weighted sum according to these weights.
Go through this weighted sum, so I'm going to...
I find it helpful to think of these weights as being some value between 10 to this weighted sum. The third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform, any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector, and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function. one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point I suppose I should say subscribe to stay notified about when that video or any new videos come out. But really,
hi, I'm Rex Moore with the Motley Fool, and I've been to a very crowded CES for 8 straight years.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have 2 main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like, well, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer. And the weights in the weighted sum defining its activation are kind of like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer. That output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the total number describing how bad those change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but
So here they go into talk about gradient descent. And are you guys all familiar with gradient descent?
I am.
Yeah.
Yeah. So it's basically say you take a you take a slope and then you just go down here along the direction where it has a steep slope. That's all. You know, this is a multiple dimension function. You take you going down. So that's why calculate gradient is so important. Once you know the gradient, then you know which direction you go. It's a steeper slope, and then you make a baby step, and then you repeat the whole thing again. And that eventually get down to the minimum. So that in essence is what they're doing here. So I'm going to make it as fast, so moving forwards.
their performance on all of those samples. Basically a valley in this graph. I'm still showing the picture of a function more bang for your buck. The way that I motivated this structure was by describing a hope that we might have, that the second layer might pick up on digits pretty well. It has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined unmoving digits centered in a tiny grid, and its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So if this is the image of what those second layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how you learn, that'll only happen if you engage actively with the material here somehow. One pretty simple recognition.
You know, very slowly in almost kind of a linear fashion. So you're really struggling to find that local minimum.
Video now.
We live in strange times.
Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with two hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes.
So this average over a bunch of lists is usually called batch. Okay, the terminology later on we'll use is called batch. You do this training one batch at a time.
This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow. So instead, you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes
So that, in essence, is the basic mechanism behind this network. Hopefully, this gives you enough understanding how this thing works. We want to watch other in this video series, but in essence, that is the procedure. What we are doing is to, in essence, is to say we go through this we set up network architecture, we go through the training, and then after training, then it's able to predict. And the network setup is basically rely on this calculating this gradient and the backpropagate. And the efficient way of doing that is to go through so-called stochastic gradient descent. So the mathematics, we won't delve into each of these things. Of course, has mathematical detail. There's a complexity behind it, and what's great things about now is to say a lot of these things are well coded, and there are a number of development platforms which basically make this kind of doing this kind of things is very well efficient. As I mentioned in the beginning, there are essentially now two, at least I'm aware, but two major platforms to do this kind of things. Now, if I go back to my the lesson link, last time, which is 2 years ago, when I taught these things, I was mostly doing going through this Google's version of that, which is using so-called Tensor Flow, and so the link here is a neural network on the Tensor Flow. So Tensor Flow essentially is a platform developed by Google for machine learning purpose, and by far this now is most widely adapted used platform. Now all this calculation are made efficient through using GPU, by parallel processing, and the most widely used GPU and more importantly associated GPU software is through CUDA's NVIDIA's GPU and with their CUDA library. Now a few years ago, Facebook came up with their own platform of software development. Is called PyTorch, and I find PyTorch is a little bit easier, seem to be more intuitive. So we're going to use this PyTorch this time go around and see. I'm going to do this together with you in the next two lectures, And so I want you at least to take a look at the Google Collab. Google Collab essentially is nearly just like Jupyter Lab or Jupyter Notebook, but you don't need to actually have your local version of the Jupyter running. It's basically just everything is based on browser, and basically Google Collab is give you online browser which can run all this Python and the PyTorch code. So that's what we want to do. And with that, I think I'm done today. So pause share, and so we're done essentially with the lecture today. Any of you get questions?
I'm kind of curious about like exactly, because we know like how the neural network functions, but like in like the sort of iterative process required to create a neural network, but like is there an intuitive way to like understand like how to design a neural network in terms of like how many neurons you have?
I think that is the part which is pretty much at the moment still us. There's no systematic way, say, for a particular problem you have on your hand, particular test, how you design network. Now, if you're experts in that particular field, maybe you have some kind of intuitive understanding, you can break down this process into certain chunks, and then you construct a network architecture which is based on this your intuitive understanding. That's one way. So that I think is a difficult part in terms of this is really is the design of architecture of that. But also fortunately there are now research in areas so-called transfer network. Now people are using. Basically, suppose you have a design, for example, which you already have trained it and designed it, which is to be very good in particular task. For example, image recognition for a dog or cat or different animal. And then suppose you want to design a network which is slightly different from that. Let's say image of a human face to distinguish whether it's male or female, or it's old or young. Then, you know, this two network has sufficient similarity that you may able to transfer from one to another. So therefore, so you often can just follow the network structure from well-established network. So that's one way to go ahead. And then of course, more ambitious one is to say, okay, I'm just going to let the network not only learn, but maybe even learn the design itself. And this is also in the modern software development that people are starting thinking about maybe not only just write the code. I'm going to write a network which can write the code. So you can think about an intelligent way to design. Maybe you can have separate network to help you design the network. So that's a lot of things one can think about it here.
Okay.
Any other questions?
No.
Okay, if that's it, then I'll see you Thursday.
See you.
All right.
All
Thank
right.
you.
Yep.
Bye.